Okay, I think it's already on. So yeah, go ahead. I'll stop my video and I will come back when you finish.
So, well, thank you very much for inviting me to this talk. And first of all, felicidades to all the Josep's, Finas, Jose's, and fathers in this room or virtual room. As Ramon said, I'm Alicia. I'm a postdoc right now in Northwestern University, working mainly in GRBs, but also I'm trying to continue my work on X-ray transients with all my Amsterdam family that were Rudy Binance, Nathalie de Renard, and Jacob van Eyden. Or well, my Dutch is not very good, but anyway, if they hear me, they are going to laugh at me. Anyway, so today, yeah, let's talk a little bit about the X-rays that I have been, like my studies in X-rays about these objects. So first of all, sorry. So first of all, I would like to say why X-rays. No, why X-rays are a very powerful tool that in science we use for studying those kind of mechanisms or structures or what science what nature has behind, and we cannot only study with our eyes. So as you can see here, we can also use our X-rays to tell the poor Mr. Frog that he has a hand inside of his body. But in astrophysics, we use our studies in multi-wavelength or multiband for getting information about different emission mechanisms, different structures, even from the same object in the universe, and especially for, in this case, in high energies, X-rays and gamma ray band, we can use this information to study one of the most violent and energetic phenomena in our universe. So why binaries? Binaries give us a lot of different snapshots and different mechanisms and let's say moments in the lifetime of the universe. So let's say, as all of us know, that stars mainly when they born, they don't born alone. They born in pairs or triples. And in this case, in a very simplistic way, because I'm not an expert in this field, but let's say if we have a binary with two high mass stars, the most massive one evolves, and in time it will collapse and form a neutron star or either a black hole. And when we have this compact object plus the high mass star, we have our high mass X-ray binary. And this will be our first snapshot of this talk. I will give two parts. In the main, you can interact me if you have questions. And then in the first part of the talk, if you want to go back, we will talk about high mass X-ray binaries. And then the second part will be more into this second part. Then when we have this second high mass star, it also will evolve and collapse again in a neutron and give birth to a neutron star or black hole, and forming this compact object binary that at the end will merge in time. And we can detect these events thanks to detections of gravitational waves, but also thanks to our satellites. We see the emission in gamma rays, and therefore we can follow up the afterglow of these events with multi-wavelength monitoring. And this will be our second part of the talk. And you, again, if you have any question, we can go on that. So let's go and focus on high mass X-ray binaries. And in particular, we will talk about a special one type called X-ray transients. So what are these X-ray transients? So X-ray transients, as I said, they are binaries where we have a high magnetized neutron star. I know that a lot of people here works in magnetars, so we are a little bit less than 10 to the, it's between 10 to the 12, 10 to the 13 Gauss. And this high magnetic field neutron star is orbiting around a PE type star. These stars are massive stars and they spin very fast, and they have periodic moments of where they eject material. And this material gets stored in the equatorial plane of the star, forming what we call a decretion disk. And this decretion disk is different from the accretion disk that forms around the neutron star. So I want to be clear with that. Decretion disk goes with the companion star, accretion disk with the neutron star. So we have this neutron star that orbits around the companion, and we can see two types of outbursts in these systems. The first one is what we call type 1 outburst, and it happens periodically. And normally, well, if you see here in this plot, we have the path intensity. We normally follow it with the path, swift path versus time. And we see these outbursts that coincide with the periastron passage. There are these vertical lines. And it happens because the neutron star is accreting material from the decretion disk of the companion star. And the normal luminosities of these outbursts are around 10 to the 36, 10 to the 37 Ergs per second. However, we have a second type of outbursts, what we call type 2 or giant outbursts. And as you can see here in this light curve, you see that these outbursts can last more than one orbital period. And sometimes even they exceed the Eddington luminosity for a neutron star, reaching luminosities over 10 to the 38 Ergs per second. The motivation of or the reason why these outbursts happen, we really don't know. But it is thought that maybe it's a composition between the equatorial plane where the decretion disk is and the orbital plane, or the decretion disk around the companion star is kind of rough, and then the neutron star can accrete more matter. Or even though sometimes they also say that could be some oscillations that happen in the accretion disk of the neutron star, but there are several, let's say, reasons why this thing can happen, but we really don't know still why they happen. But what is clear that you can see here, type 2 outbursts are different from type 1. And the fact that we have type 2 outbursts doesn't mean that we cannot have type 2, because at a certain time, you again see the activity from the system. So this is very nice. We have a lot of data in outbursts and when you have high luminosities. However, the question here is that what happens to the systems when they are not accreting, and especially when the neutron star is close to the apastron of the orbit. So this is the aim of the project was like, okay, let's go and push to the limit our data and see what can we get. So some of the questions that we were asking ourselves when we were doing this project, it was like, if, for example, like X-ray transients are detectable when they are not in outburst, if they show similar activity, and especially if these high mass X-ray binaries with high magnetic field neutron stars show similar behavior to those that have low magnetic field neutron stars in the low mass X-ray binaries. And our conclusion was that, as always, the neutron star spin period and the magnetic field strength are key components in these systems. So let's go a little bit further and see what theory or what different scenarios we can find in these systems. So when we are not in outburst, one of the scenarios that we can find is what we call the propeller regime. And if these systems enter in this propeller regime, if they can have the kind of low level accretion. So what happens in this propeller regime is that when we are in outburst, especially in this kind of giant outburst, the flow of matter is high. So this can overcome the magnetospheric barrier that is formed by the combination of the neutron star spin and the magnetic field strength. But once the accretion flow starts decreasing, this magnetospheric barrier starts becoming very important. At some point, the matter cannot enter anymore. They cannot overcome this magnetospheric barrier, and the material is expelled out. Therefore, we expect not to see any kind of accretion of matter onto the magnetic pole of the neutron star. This was one of these scenarios. So how it is translated in what we see is in our light curve, we see like a rise during the outburst. And once the accretion flow decreases, we see the decrease in the X-ray luminosity. And when the propeller regime enters in game, we see that the a suddenly change in the decay and a steepening, no, in the slope of this decay. And what happens here, we have some ideas, but we put it in a question because we will see further what happens there. The other scenario is the heating cooling scenario. So this scenario was really like studied in depth for low magnetic field neutron stars. So we are saying 10 to the 9 Gauss. And what is happening in this case is that and this is for low magnetic field neutron stars, is that before the accretion or the outburst, the crust and the core of the neutron star are in thermal equilibrium. What happens is that when we have the accretion of matter on the surface of the neutron star, the matter starts being, let's say, piling up on the surface, and this compresses the inner layers of the crust. And what happens there is that it triggers some nuclear reactions, and these nuclear reactions release energy and therefore heat, and the crust starts heating up, but the core still gets, it takes more time. So this thermal equilibrium is broken. And what we see during outbursts is like a rise in the X-rays. But once the outburst stops, then crust and core try to restore this thermal equilibrium. And for that, the crust releases the emission, like the energy, and we see it as emission of cooling from the surface. And this is translated in a thermal emission. So what we see is that with time, the temperature of the surface of the neutron star decreases. Okay, this is good for low magnetic field neutron stars, but we really didn't know if this was possible for high magnetic field neutron stars in X-ray transients. And because this magnetic field is so high, the magnetic field enters has very important role inside of the crust. So one of the ideas is that maybe the magnetic field lines enables the reactions to happen in the surface, and maybe they happen under the lines of the magnetic field, and therefore the inner part of the neutron star was hotter than the rest. Or maybe the magnetic field lines don't allow these reactions putting all the energy towards the core, and therefore we see a hotter surface than inner parts of for the neutron star. Or maybe the magnetic field has strange configurations inside of the crust, and therefore we still don't know what is happening there. So for that, what we did is to have our X-ray observations and then try to upgrade this code called NSCool that they use for low magnetic field neutron stars, and see if what was the special key component that was the magnetic field. So now the point is we are upgrading this code for putting the magnetic field strength, and then the next step would be to introduce the configuration of this magnetic field in the crust. So let's go and talk about the third scenario, and this is called the coldest scenario, and this is an idea that was already introduced some years ago, I think 5. Oh my God, time passes so fast. So in the cold disk, this happens for certain neutron stars, and therefore especially slow rotating neutron stars. And for these neutron stars, the propeller regime is, let's say, for reaching this propeller regime is very hard because they spin very slow. So what happens is that the accretion disk around the neutron star gets, after the outburst, has time to cool down. It has low ionization and low viscosity. So therefore, the accretion disk, or let's say the matter in the disk, can penetrate more and more the neutron star magnetic fields. The lines of the magnetic field the lines of the magnetic field of the neutron star. And once it's getting closer and closer, the material gets ionized again. And Then remember, it doesn't enter in propeller regime. So at some point, it can start like a stable accretion to the magnetic poles of the neutron star. How is this translated is that during outbursts, we see again the rise. And then at some point, when it decreases, we see a stable decay of the X-rays. And this is due to this cold disk accretion. However, what happens is that, again, when it crosses again the periastron passage, this accretion disk is repleted again with material from the accretion disk. And what we expect is to see continuously this kind of behavior from the system. So let's see, this was the theory, let's see what we see. So let's go and focus on fast rotating neutron stars. And for us, fast rotating neutron stars are those ones that are less than 10 seconds. So we follow, for example, this system for U0115 with Swift and XM Newton. So this system showed like a giant outburst in 2015. And as you can see here, we have the BAT in black and the Swift in red. And then in green here, we have XM Newton. I'm sorry for the people that are colorblind. And then we see that it was detected that the system was entering the propeller regime. So as you can see here, there is a suddenly change in the decay of the outburst. But after the propeller regime, you see here some kind of emission. And our question was like, oh, if it is in propeller regime, in theory, the matter is not reaching the neutron star surface, what is happening there? And what is happening there is what, and it also, this emission was above the quiescence level of the system. So what we see there is what we call the cooling from the neutron star. And this cooling is detected also, we see a decay in the luminosity and also in the temperature. And as you can see here, we see the luminosity decaying, the temperature decaying. This is our XM Newton observation. The radii from this emission region is small, so that's why we know that is from the pole of the neutron star. But what happens here is that suddenly this luminosity and temperature went up, and we were like, oh, what is happening here? If it is cooling, why the temperature is going up? So if we see 1, 2, and 3, and we put these numbers again in our lecture, here 1, 2, and 3, you see that 1 and 3 are obtained, this observation, and are obtained close to the periastron passage. And number 2 is in the apastron. So what we think is that there are several mechanisms in play, is that in 2, we really see the cooling of the neutron star. And in 1 and 3, what we see is accretion, or low, like in this case, low level accretion due to the periastron passage of the neutron star. So the propeller regime or the propeller effect from these systems are not 100% effective. Let's go and talk about slow rotators. What happens to these slow rotators, those that are spinning are above 100 seconds, no? We said that they accrete from cold disk. And as you can see here, for GRO1008, we have this type 1 outburst during periastron passage. And then you see this constant emission after outburst. The propeller regime of this system, as you can see, is at this luminosity, so it will never be reached. And just for an example, the 4U115 quiescence level was at this level. So this emission is several orders of magnitude above this quiescence level. So what happened is that we continue another source, the X304-1. You see here some type 1 outbursts, and we can see here some kind of accretion due to cold disk. But what happens here is that we don't have any other outbursts, and this source hasn't been accreting since I think 2017. But we still detect the emission from this system. And indeed, if we go here, we see like a constant emission. And we also got some new star observations at apastron we detect pulsations, and we see that the spectra is hard, but it's different from the outburst spectra. So this is a different kind of accretion due to a cold disk, but we know that it's accreting due to the detection of pulsations and also the hardness of this spectra. And then we have the intermediate rotators that we really don't know what happens there. They are between 10 seconds and 100 seconds. They show outbursts, but also they show kind of reflaring activity. And this reflaring activity sometimes is not even related to the periastron passage, as we can see here in vertical lines. And we need still to further investigate these systems, but it can be like due to these instabilities and also maybe the extension of the accretion disk of the companion star. So for takeaway message one is that we need monitor these systems in low X-ray luminosities. They show a different variety of behavior, but what we know is that fast rotating, they enter propeller regime and show cooling emission. Slow rotating neutron stars, they show accretion from a cold disk, and the intermediate rotating neutron stars, they show reflaring activity after outburst. Then if we could get more multi-wavelength observations from these systems, maybe we can disentangle more what is happening there, since we are ignoring the companion star, what is happening to the companion star in these X-ray observations. So this is the first part of the talk. So if you have any question. I don't see if there is hand or no. Okay, I continue.
Yes, go ahead. If there's a questions, I will tell you. Don't worry.
Okay, thank you, Rama. Okay, so let's go and talk about the compact object binary merger. So I told you that we can detect these events thanks to the detection of the gravitational waves, but also we can detect them thanks to the emission from gamma ray bursts. So what is thought here is, well, we all know, well, not all, sorry, about the gamma ray bursts are energetic explosions, no, that happen, you know, at cosmological distances, and they happen at with an isotropic distribution. So it is thought that or it's known that the gamma ray bursts are divided in two families or two populations. And this division is based on the duration of the signal of the burst in gamma rays. So we have short gamma ray bursts and long gamma ray bursts. So for short gamma ray bursts are those that last less than 2 seconds, and they are less than energetic than long GRPs. And they happen normally in lower density environments, and they show big offsets from the host galaxy. And the most important thing is that for some of the short GRPs, it is let's say the progenitor are the double neutron star binaries. And this is known because we have the detection of this gravitational wave event, 170817, and it was simultaneously with a short gamma ray burst. For long GRPs, however, the duration are more than 2 seconds. They are very energetic, and they are found within the host galaxy. And the progenitor of these bursts are very massive very massive stars. And this is also related because when you have a long GRB, most of them have supernova related to supernova explosions with these events. And as you can see here, the number of bursts versus the duration, we see short GRBs and long GRBs. And in the middle, this division is not a sharp division. We still have some events that are within both families, and this is very important for the next slides, because I will talk about a case that was just there in the middle. So, and we didn't know if it was short or long. And we tried to put all the pieces of the puzzle and get with the final conclusion for the classification of this event. But before that, I would like to introduce you a little bit of this jargon that I'm going to use. So when we have this neutron star binary, neutron, and then the neutron stars merge, we see the source GRB, or the emission in gamma rays. And then what is expected is that the central engine launches a highly collimated and relativistic outflow, what we call jet. And this jet interacts with the medium. And because of this, with time, the bulk Lorentz factor of this jet decreases. And at some point, the value of this Lorentz factor will equal the inverse value of the opening angle of the jet. So what is happening here is that if we draw the light curve in X-rays, we see a decay in X-rays and then suddenly a change and a steepening of the decay. And this moment is when we see the jet, and it's what we say jet break. And if we get to know this time, we can calculate the opening angles of these jets. And therefore, we can get and infer a distribution for these opening angles and get a rate for source GRBs. And we can get some knowledge about the rates of these events, therefore the rates of double neutron star mergers, and we can to make a comparison of this rate with those from LIGO or from studies from our galaxy. But let's go and talk about 1804-18A. So this GRB was detected by all these observatories and for spacecrafts, by spacecraft. So it was followed by Fermi and Swift. And what we see is that the Swift duration is in the limit of between short and long, but it was short, it was 1.9 seconds. However, for Fermi was 2.5 seconds. So there is it's not the same, and also like it's incongruent, it's ambiguous case, because if it is short, it's a long duration one, and if you can see, it's quite less hard than for the population of short GRBs, which are in red here. And if it is long, it's a short duration, it's a very short duration. So if we plot all the hardness, like all the hardness and durations from GRBs detected by Fermi, we see that our GRB is living in between both populations. And just for reference here, you have 1708, 17A. So it is kind of in the same area. And then if we can calculate some probability, if we draw a probability of this event being short, and it's a 60% probability. So it's not 100%. So we need more information to see if it is short and long. If it is due to maybe a merger of a short neutron star binary, or if it is a long GRB. So let's go and talk a little bit about Swift and Chandra observations. So from Swift, we see that at the beginning there was a decay in X-rays, but suddenly there was like a kind of plateauing. And this is not, we don't expect this thing from GRBs for the afterglow in X-rays, because we expect to decay directly. So we expect, we did an inspection of our Chandra observations at late times, and we see that the afterglow was detected, but also you see here like a kind of extra source, and is within the source emission, the source area of XRT. And if you can see here, we cannot differentiate in XRT data both sources. So what was happening is that at late time, like we were seeing the X-rays from the afterglow of the GRB plus the contaminating source. So what we did is to remove the flags from this contaminating source and only take the X-ray afterglow. And as you can see here much better, we see that there was a fine and good decay as a single power law. The level of the contaminating source influx is here, and our detections go even farther. And the most important thing is that this GRB was detected up to almost 39 days. And this is very weird for short GRBs, because short GRBs are expected to decay in early times, so like around 1 between 1 and 10 days, is expected not to have X-rays. So for comparison, let's put another piece of the puzzle. We want to know if this X-ray behavior is similar to short or long GRBs. So what we did is to get all the long GRBs and short GRBs with known redshifts from Swift and to plot all together. So we have luminosity versus the rest frame time. And we see here in stars or the afterglow of our GRB. And again, you see that is very in between both populations. So what we did is to have two slices of time, one at early times and the second at late times. And we took some, not random, but I will tell you why these redshifts in a while, but we consider 1 and 1.5. And we see that for early times, our GRB was kind of at the beginning of the long GRB family population. However, it coincides with the short GRB population. However, at late times, we see that it really goes into is embedded by the long GRB population. So there is, again, an ambiguous case here, but I would like to say that in this case for late times, it could be a potential bias because we don't have enough information from short GRBs at late times. So what we might need is more following up with Chandra and XMEM at these times for short GRBs and to see how they behave. So in Optical, we use our UCART, MMT, and Gemini, and we see that the afterglow was detected till 5 days. And what is happening here is that almost at 289 days, we see something there. And this thing that we see there is the host galaxy. And we can determine the host galaxy redshift. We can infer some lower and upper bound, and it's between 1 and 2.25 redshift. The upper limit comes because the afterglow was detected also in UV by UVOT. And this put the Lyman limit alpha, the Lyman limit at this redshift. With this all information, we put all together, also with all the other data that was published for this GRB. And as you can see here, we have a very beautiful light curve in different bands. And what we can see is that, again, these afterglow light curves, they don't show a break. So we don't say a jet break. And it goes also as a single power law as it was happening for X-rays. And here, this is something extra, but anyway, at very early times, there is like a pump. And this is what was already mentioned by Becerra et al. In 2019, that could be something called reverse shock. And thanks to our monitoring at late times, we could, and our modeling, we can confirm that this is the first GRB with a reverse shock and especially detected in optical band. And last time, one of the last pieces is that our energy and density, we can draw some values, but because the X-rays and the optical data are in the same, let's say, segment of the spectrum, this space parameter is generated. But anyway, we can draw some values, and we got energies and densities that are in agreement with the short GRB population. And from these values, we can also get some lower limits for the jet opening angle that we can get and put together with all the information that we have for short GRBs. So we can use this kind of data in a next project that we are doing for getting some rates for short GRBs and comparing them with the LIGO rate that we get. But as I said, we weren't still very sure if it is still short and long, and this was the final piece of the puzzle. So if we plot all together the energy in gamma rays, the energy in gamma rays, and the energy peak from the spectrum, we see that our GRB really falls within the family that is followed by the short GRBs. these red ones are long GRBs, these are short GRBs. So this was the last piece of information that we needed to say, okay, 180418 is a limiting case of short GRBs, of a short GRB, and we have a wide opening angle, at least for the jet opening angle, between 9 and 14 degrees, because we don't detect this decay, this steepening, no, in the light curve. So these are my other conclusions. 180418A is one of the short GRBs that has been detected up to 40 days. We detected a reverse shock, and we also find a host galaxy for this GRB that normally is very difficult to find host galaxies for this kind of events. And with all of that, my takeaway message is that we need more multi-wavelength observations of these events, because without multi-wavelength observation, we weren't able to, classify this event. And we will need more monitoring at late times, especially with Chandra and XMM, to get some populate this area from here for short GRBs and get more information and distinguish between short and long GRBs. And with all of that, thank you for your attention and for giving me the opportunity of talking to you about this science.
Thank you very much, Alicia, for this nice talk. So now, are there any questions? If you have question, go ahead and mute yourself and ask the question, or you can also raise your hand and I will tell you to speak.
I have a small question.
Okay.
I don't know how to raise the hand, sorry.
Go ahead.
Ali, thank you for the talk. It's more like a curiosity on the first part with the high blah, blah, blah. So if I'm not wrong, you estimate the magnetic field of this system through resonance scattering the cyclotron feature, right?
Mm-hmm.
And do you know if there are other methods to estimate the magnetic field or only this one?
So for being really like, how to say, concise with these things, we use the cyclotron, like the line.
Okay.
Yeah. Sorry, we can get some.
Sorry.
No.
For how many systems do you have an estimate of the magnetic field?
Well, I think at least for I'm following like kind of 20 of them. We have values of this, but again, also there is a little bit of because sometimes it depends on where, let's say, the height or in the column density in the pole where they are formed. So there was some work done by this Alexander Mustikov that there is some variations, no, in the strength of the magnetic field, depending on the height of the column where they are formed. But yeah, mainly those, and then we can get some estimate. Like if we don't know, we get more or less like we get between we give this 10 to the 13, 10 to the 12 Gauss.
Thank you.
Any other question?
I have a question.
Go ahead.
Thank you very much for the talk. I have a question about the reverse shock. I know that if the medium is too magnetized, it's hard to have a reverse shock. Do you have an idea about this detection of reverse shock does allow you to put limits on magnetic field of the medium? Or?
Yeah, we got, well, we get some values for this value of the fraction in the magnetic field. of the medium, but especially was also because the density environment was very low. So we could also kind of constrain those values. But still, there are like, it's not I don't have the number. But yeah, with this modeling, we could also get some values for the fraction for the parameter for the magnetic field. The low density, we could also get that value, and also for the some value for this bulk Lorentz factor.
Okay. And the value of bulk Lorentz factor, for example?
It was 150, if I'm not wrong. Yeah.
Okay, thank you very much.
You're welcome.
More questions? No? Okay, then we can thank Alicia again for the talk and for agreeing, participating to the pizza seminar. And very well, see you next week for the next pizza seminar. And thank you, Alicia.
Thank you very much for your time. And now pizza time.
Yes.
Yeah. Thank you very much.
Bye-bye.
Bye.
Thanks a lot. Very nice talk.
Ciao, Nanda.
Yeah, very nice talk.
Bye. Thank you.
Ciao,
Bye.
Chicho.
Bye-bye.
Ciao, Ali.
Ciao.
Gracias, Ramón.